Okay, so our focus in this lesson is going to be on integrating expressions that are a little more complicated or complex. Even though an integrand might be complex or a little bit more involved, doesn't mean that it doesn't mean that it's got to be complex or complicated when finding the antiderivative. But we're going to look at using a substitution rule. So if we look at this example, or this integrand, the 2x times the square root of 1 plus x squared dx, this integrand does not have its own little nice pretty little antiderivative. So this is using a substitution approach gives us a way to integrate complex expressions. So here's the idea. I'm going to pull that down. The idea behind substitution is to replace a relatively complicated expression or integral by a simpler one. The challenge is to actually think or determine an appropriate substitution. So here's how you kind of look at this. You want to choose an expression within the integrand whose derivative is also in the integrand. So for now, I'm going to just kind of point it out. If you look under the radical, you have an expression of 1 plus x squared. If you were to take the derivative of 1 plus x squared, the derivative of 1 is 0, so you lose that piece, but the derivative of x squared is 2x. And notice that we do have a 2x in the integrand. So that's kind of how you want to look at it. I will tell you that choosing the right substitution does take practice. If you try something and it doesn't work, then try something different. So if I had tried, hey, let's let u equal 2x. Well, what's the derivative of 2x? The derivative of 2x is 2. Well, that doesn't help me any. And so then I would maybe then focus on 1 plus x squared. So that's what I mean by if you try something and it doesn't work, then go back to the problem and try something different. So I'm going to kind of pull away, and I want us to take a look at this example. And I've noticed that I have a typo here. What I notice is that this 20 right here should be a 4. Okay, so in your notes, if you see that, you might want to make that a 4. So here's what we've got. I want us to take the integral 20x to the 4th divided by 4x to the 5th plus 3. And I'm actually going to help us out. I'm going to say let's let u equal, for our u substitution, let's let u equal 4x to the 5th plus 3. Now let me talk about why I chose that. When I look at 4x to the 5th plus 3, I notice that the derivative of 4x to the 5th is going to be 20x to the 4th, which I have right there. And then the plus 3, the derivative of the 3 piece, is just going to be 0. So I'm going to let u equal 4x to the 5th plus 3. I'm going to need du over dx. So the derivative of u with respect to x will be 20x to the 4th. Okay, so I want you to consider something. If I were to take this du over dx, if I were to multiply both sides by the dx, I would be left with du equals 20x to the 4th dx. And on my original, I left off the dx. So when you're using a u substitution, you need to determine a u, which I've provided for us, and we need to find the derivative of u. So now looking at, we have what we need to rewrite this expression in a simpler form to be able to find the antiderivative, and we'll see what happens. So notice that we have, okay, so I see 20x to the fourth dx. So this piece right here, excuse me, that piece right there is actually going to be replaced with du. So I have an integral, I have a du, and then my denominator was 4x to the fifth plus 3, and I'm going to replace the denominator with u. So what I have is I have an expression, or I have an integrand that no longer involves x's but involves u's. And the version, the integrand that involves u, is a whole lot cleaner and a whole lot easier to work with than this garbage. So what I'm going to do is I'm going to rewrite this as the integral of 1 over u times du, which is the same thing. And now for me, it's easier to see that I have 1 over u, which I know has an antiderivative of the natural log of u. Don't forget your absolute value. And then this is an indefinite integral, so I will add c. So now what I have is I have the natural log of the absolute value of u plus c. And all I have to do now is replace my u's with their x's. So my final result then is going to be the natural log of the absolute value of 4x to the fifth plus 3, and then plus c. So I took a relatively nasty expression, a relatively nasty integrand, and I've rewrote it in terms of u, which turned out to be much simpler to work with. And so anytime you can rewrite an expression in something smaller or more simple, it definitely makes the process a little easier. Okay, our next example is going to be this one, which is, and I'm going to scoot my page up once I rewrite it. So I want us to find the antiderivative, or I want us to integrate 80x to the third times 3 raised to the 5x to the fourth minus 2 power. Whew. And I have said that let's let u equal 5x to the fourth minus 2. Okay, so now I'm going to see how we can work our magic on this. Ultimately, if we know we're going to find, we're going to need the derivative of u. So du over dx is equal to, what, 20 x to the third. Okay, well, I see the 20x. I've got 20x to the third. If I swing the dx over, I get du equals 20x to the third times dx. Okay, so I see something that looks a little off. And once again, I left off the dx. So I have a 20 x to the third times dx, yet I have an 80 x to the third. So what if, how can I get that to be a 20? What if I were to bring out, well, I tell you what I'm going to do. This is what I'm going to do. I'm going to actually bring the 80 out because it's a coefficient of x to the third. And I'm going to have it as 80 times the integral of x to the third times 3 to the 5x minus, 5x to the fourth minus 2 power dx. Okay, so I brought the coefficient of 80 out front. So now I've got this x to the third dx, but what I don't have is the 20. So if I need the 20, I'm going to put the 20 in there, but if I put a 20 in here, I have to put the 1 over 20 on the outside. So a little extra work, but still nothing major. So 1/20 of 80 is going to be 4 on the outside times the integral of. All right, so I have the 20x to the third dx, the 20x to the third dx. All of this, that's going to get replaced with du. Now what I have here is 3 to the 5x to the fourth minus 2 power. Well, what did we say about 5x to the fourth minus 2? We said let's let that equal u. So what I have now is I have taken this relative complex expression, and I have simply taken all of that and I have rewritten it as simply 3 to the u power. Now 3 to the u power has its own little nice antiderivative, and so that would be, if you recall, it would be 3 to the u over the natural log of 3. So I have 4 times the 3 to the u over the natural log of 3. I'll add my c, and then all I have left to do is go back and replace u with the 5x to the fourth minus 2. So 4 times 3 to the 5x to the fourth minus 2 over the natural log of 3 plus c. So that relatively nasty expression I was able to rewrite simply as 3 to the u. And so how did I know to choose 5x to the fourth minus 2 as my u? Well, I knew that x to the third is the derivative for an x to the fourth, and so that's just kind of how I started. Okay, now let's go back to the example that was at the very beginning. So we started out with the integral of 2x times the square root of 1 plus x squared. So let's talk about what a good u value expression would be. So let's let u equal 1 plus x squared. Now, I'm not using the square root of 1 plus x squared because if I did, think about what that derivative would be. That derivative would be really, really nasty. So I'm just going to let u equal 1 plus x squared. I know that I will need du over dx, which will be 2x. If keep forgetting to write that down. If I multiply the dx over, I get du equals 2x dx. So now I've got this expression, my 2x and my dx, they get replaced with du, and I have the square root of this expression, which is u. So I'm now simply looking at the integral of the square root of u du. And so I took this expression, I have rewritten it in a little simpler form, and now taking the square root of u and looking at it as u to the 1/2, then this turns out to be 1/2, 3/2, 2/3. So 2/3 u to the 3/2 plus c. And now just go back in and replace u with 1 plus x squared. And I get 2/3 times 1 plus x squared to the 3/2 power plus c. Okay? So, it's all about trying to identify something to let u equal. And letting u equal something that has its derivative is in the in the integrand is where you really want to try. Well, if we look at the next example is very similar to this one. Our next example is simply the integral of the square root of 2x plus 1 dx. Well, you might be thinking, I don't see anything that could possibly be a derivative. Well, let's let u equal, let's just start somewhere. Let's just let u equal that stuff under the radical. So if I let u equal 2x plus 1, then that means du will be 2, and I'll go ahead and put my dx there. Now I think I begin to see something. I have this 2 dx, well, I have a dx, and because this is simply 2, I'll put a 2 in front. But if I put the 2 there, I also have to bring this out front, 1/2 to offset it. So now I have the 2 dx, which is 2 dx. I'm replacing these two pieces together with du. I have my integral, and now I have the square root of whatever I let 2x plus 1 equal, which was u. So now I'm looking at 1/2 the integral of the square root of u du. Now, just to kind of stop for just a second, why did I put the 2 here? Well, I put the 2 here so that I could have a du expression. Without the 2, I can't use this 2 because it's attached to the x, which is a part of u. So I created my du by multiplying by 2 and then multiplying the outside, or by multiplying by 1/2. That offsets it. So now this turns out to be my du piece, and I have the square root of the u piece, which is what I have here. All right, so finding the antiderivative of u to the 1/2, we actually did it up here. So u to the 3/2 times 2/3 plus c. I like that those 2's cancel. And now I have u to the 3/2 over 3 plus c. And let's see, I will now go back in and substitute 2x plus 1 for u. So 2x plus 1, excuse me, to the 3/2 power, and that's over 3 plus c. Now, you might see this written as 1/3 times 2x plus 1 to the 3/2 plus c. So there you have it. Okay, so it's a matter of finding an expression to use so that you can find the antiderivative a lot easier and a lot quicker. Okay, so I'm going to actually skip over a couple of problems and go down to the very last example, because I think the others are pretty straightforward. I think you can follow them in the notes. But let's look at this one. Here I have the integral of tangent of x secant squared x dx from 0 to pi over 3. Okay, looks like a pretty... My first thought might be to write secant squared as 1 over cosine squared, but multiplying that by tangent, it doesn't get me anywhere. So I do, though, recall that secant squared x is the derivative of tangent of x. So I am going to try this u substitution. So I will let u equal tangent of x. Du over dx will then be secant squared x. Swing the dx over, and du equals secant squared x dx. So now I have my secant squared x dx, which is this piece, So this is going to get replaced with u. I'm sorry, this is going to get replaced with du, and my tangent will get replaced with u. So what I have now is this. I have u for tangent, and I have times du for the secant squared dx. Now, there's a reason why I have not brought the 0 to pi over 3 over onto this integral. And I'll explain why in just a minute. I want us to go ahead and find the antiderivative of u du, which will be u squared over 2. Now, this is a definite integral, so I'm not going to add c. I know that I need to, I will use the first part of the fundamental theorem of calculus where I get to evaluate. But here's where you have to be careful. I'm not going to evaluate this expression from 0 to pi over 3, because 0 to pi over 3 are the lower and upper bounds for x, not u. So here's what I'm going to do. I'm going to replace u with what it equals, which was tangent. And I'm also going to do this. I like to do it this way. 1/2 times u squared will equal 1/2 tangent of x squared. Now I will evaluate that expression from 0 to pi over 3. So now when I evaluate, I have my 1/2 times tangent of pi over 3 squared. Did I do that right? Yes. Minus tangent of 0 squared. Yeah. And now 1/2 times, okay, tangent of pi over 3 is going to be the square root of 3. Square it. The tangent of 0 is 0. So basically this reduces down to 3/2. Okay, and if you need to go back and look at this, remember your circle, evaluate tangent of pi over 3. Now, I will say that we could have gotten away, we could have actually kept our expression in terms of u. We could have bypassed all of this since it's a definite integral, but what we would have had to have done first is we would have to change the lower and upper bound to represent u and not x. So what could we have done? Well, what did we say u equaled? Tangent of x. So if I evaluate tangent of 0, that's going to give me 0. So that would be 0. And if I evaluate the tangent of x at the pi over 3, our circle, pi over 3, 1/2 square root of 3 over 2. Pull that down just a bit. Sorry about that. And the tangent is the square root of 3. Then my upper limit would be the square root of 3. So right here, I could have changed my lower and upper bounds to go to represent u and not x. And so when I then go from here, u squared over 2, from 0 to the square root of 3, then we're going to evaluate it the very same way by substituting the square root of 3, square it over 2, and subtract u squared over 2. Well, all of that is 0. And what do you get when you square the square root of 3? You get 3 over 2, which is the same thing here. So, do you have to change them? No. But you need to know that it's a possibility, especially when you have a multiple choice type question. So you have to be careful about that, especially when it's a multiple choice question. So that's that is how you use U substitution. And there you have it.